Using heat of fusion or heat of vaporization to find the heat needed to melt or boil a substance. So essentially what you're doing for this kind of problem is a heating curve can help you visualize it. You are going to add Q for whatever steps of the heating curve that you are observing. So usually a heating curve is something along the lines of temperature against heat added Q, okay? And you'll see the general kind of shape is going to be something a little bit like this. So phase one is going to be heating a solid up until you get to the melting point. So then you're going to have like a flat line, and that is what is happening during the melting, because while something's actually melting, all the heat added is not going to raising the temperature, it's going to increasing the kinetic energy of the molecules or atoms in your solid until they melt. And then you're going to add more heat, which will go towards raising the temperature. So this is a hot liquid getting hotter, and then you're going to reach the boiling point. Okay, that's usually a lot longer than the melting point, because think of the energy difference between the liquid and the gas phase or something. Okay, so then all the heat added at this point is just going into boiling the liquid, not into increasing its temperature, and then you're in the gas phase, and any heat added is just going into raising the temperature of the gas. Okay, so the lines that are have a positive gradient is a solid getting hotter, a liquid getting hotter, and then a gas getting hotter. So for those portions, you're going to use what you already know, which is going to be, so this is zones 1, 2, and 3. Sorry, 1, 3, and 5 even, if you like, if I'm going to number these. You're going to use what you know about heat capacity. So Q equals M, the mass, times the specific heat capacity times delta T. So just looking at units, specific heat capacity is in joules per gram per degree Celsius. I'm just going to write this underneath like so. And delta T is obviously going to be in degrees Celsius, or alternative units is joules per gram per Kelvin. Delta T is in Kelvin. Those are equivalent units, right? Because the difference in a degree in Celsius or Kelvin is the same, because the size of a degree Kelvin and Celsius, don't call it degrees Kelvin, but a size of a Kelvin unit and 1 degree Celsius is an identical unit. They just got a different 0 point. So whenever you're dealing with delta degree Celsius or delta Kelvin, you don't have to worry about like converting between the two. Saves you time, right? So mass is in grams, obvs. So then, in terms of our unit calculation, Celsius is going to cancel out. I didn't write grams, I wrote M. That's supposed to be a G, right? G, G. Mass is in grams. I don't know if that's going to work. It's just going to look a mess. So grams is going to cancel each other out. That's talking, right? So Q is going to come out in joules, okay? So that is going to apply to whether we're heating up a solid, heating up a liquid, heating up a gas. But be aware, specific heat capacity will be defined for the solid, liquid, or gas phase of something. So make sure you get the right one, right? So then what about section 2? Section 2 is melting. Section 4 is boiling. So those are going to be related to enthalpy of fusion or enthalpy of vaporization. Okay, so delta H fusion for melting. That's going to be in kilojoules per mole, right? So kilojoules per mole. So if you multiply it by the number of moles, that will give you an absolute value of like the amount of heat. So we can write our own equation. N for the number of moles times delta H of fusion is going to tell us how much heat we generate during melting. Same dealio for if we are boiling, okay? So except that'll be delta H of vaporization, okay? So I guess I should label it. This is what we'd use if we're in section 2. This is what we'd use if we were in section 4. Bearing in mind, be careful that our Q is going to come out in kilojoules on those sections. And for 1, 3, and 5, it's going to come out in joules. Look at the units, okay? And I should also add, okay, so this is for sections 1, 3, or 5. So that's if you're given specific heat capacity. You might be given values of molar heat capacity. So molar heat capacity, don't freak out, is usually C subscript M or C subscript P, depends on what textbook you're using. So the units of molar heat capacity, one subtle difference is joules per mole per degree Celsius or moles per Kelvin, and I don't know why. Did that just auto-correct me? How rude. So in order to cancel out the moles, you multiply by number of moles. So the one thing I've seen that people can do wrong here, okay, is use specific heat capacity and multiply by number of moles, or use molar heat capacity and multiply by mass in grams. So this is the same two equations, right? Just with different units of heat capacity, right? So specific versus molar. So make sure you get that right. So in this particular question, you are going to have to use the ALEKS data tab to look some stuff up, and you're going to have to calculate some stuff yourself. So which bits of the heating curve are we actually looking at here? We are asked to melt a certain mass of hexane, solid hexane, in case we didn't get the memo from melt, and bring it to a temperature of 45.5 degrees Celsius. So we need to know if 45.5 degrees Celsius is like above the melting point. I guess it is, right? So first thing you're going to have to do is look up the melting point of solid hexane. So go into your ALEKS data tab. Unfortunately, I cannot do that from this screen, but don't worry. I've got the internet. The melting point of hexane is dum 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 minus 95.27 degrees Celsius. Okay, so if that's our melting point, and then we're bringing up to a temperature of 45.5, now we know which sections of the heating curve we're actually looking at. So the first thing is we have to melt. Melting occurs at constant temperature. Okay, so you must already be at the melting point, and then we're going to have to heat. So some portion of this heating curve until we get to 45.5 degrees Celsius. I guess I need to check one more thing, which is what is the boiling point of hexane. So let me just check that real quick. Da-da-da-da, internet machine. What's the boiling point of hexane? Boiling point of hexane is give it to me in Celsius. 69 degrees Celsius. Okay, so that's above 45.5. Worth checking, because like if we'd gone above the boiling point, we'd have to add that in as well. Okay, so 45.5 is below the boiling point of 69 degrees Celsius, so we are gravy. So we're going partially up this section through the heating curve, but we're not reaching the boiling point at 69. Okay, so the other thing then we would need to do is look up the specific or the molar heat capacity of hexane. I believe that ALEKS has the molar heat capacity listed in the values. Okay, so CS of hexane is 2.27 joules per gram per degree Celsius. So you can always check the units if you're like, oh, is CS specific or molar? Look, it's specific because it's got grams. So that means for section 3, we can just use the mass in grams of hexane and the delta T we can work out in a minute. So that's okay. I think we have all the information we need for that apart from working out the delta T. So we need the melting point of hexane I've got. Okay, so the delta T, the difference in temperature, and again, because it's a delta T, you don't have to like convert both of these to Kelvin, right? You can just do the difference between the two. So 45.5 Celsius minus, this is where you got to be careful because it's minus 95.27. The difference between those two numbers is 140.77 delta degrees Celsius, okay? So that would be the same if I'd converted both to Kelvin, right? Because I would have just added 273 to both those numbers and then done the subtraction and still would have got the same difference between them. Okay, so we've got a delta T. All right, so we are starting off where we are melting, and melting is going to be related to enthalpy of fusion. So we're going to have to look up the enthalpy of fusion for hexane as well. So delta H fusion for hexane, if you look it up in your ALEKS data tab, you get 13.08 kilojoules per mole. All right, so we're going to work out for part 2. So I'm going to call this Q of melting, or Merly, because I can't type. So Q of melting is going to be N times delta H of fusion for hexane. I don't know the number of moles, so I'm going to just move that down and leave myself a little bit of a space. Okay, so my number of moles of hexane, I'm going to need my molar mass of hexane. My molar mass is 12 times 12.011 something, plus, let's see, 6 times 12.011 plus 14 times 1.0079 equals 86.1766. Okay, you may vary if you're looking at a different periodic table. I'm using the one which is in my brain. Okay, so then N is going to be how many grams? 55.5 grams is my actual amount. So the trick I always teach people is to write your molar mass out as a equivalency. So 1 mole of hexane weighs exactly 86.1766 grams, and then it's very easy for me to see that I've got to put the grams on the bottom of this conversion factor instead of being like, do I multiply by or divide by the molar mass, depending which direction I'm going? I'm just going to do this, right? If you write an equivalency, then a unit conversion factor, your units are going to be correct because I'm going to end up with units of moles of hexane, and that's going to shake out to be, let's see, 55.5 divided by 86.1766, 0.644026, blah, blah, blah. I'm going to leave quite a few sig figs there, that's fine. Okay, so then I can use that number to calculate Q melt. So that's going to be this number of moles times delta H of fusion, which was I'm trying to look at it, 13.08 kilojoules per mole. Okay, so if I then do that times 13.08, that is 8.42. I'll leave another decimal point, 424 kilojoules. The moles are cancelled out, right? So this is for section 2, right? The melting. So then the next thing I have to do is my heating of my liquid, right? In section 3. So Q heat, I guess. Actually, that's confusing. Let's Q liquid. Let's call it Q liquid, okay? So that is going to be based on my specific heat capacity. So that's M times delta S times delta T CS. Okay, so we don't need to use the moles this time. We're just going to use the mass in grams, which is 55.5 grams, because that's going to cancel with my specific heat capacity, which is 2.27 joules per gram per degree Celsius. And then we already calculated the delta T as being 140.77 degrees Celsius. So unit-wise, we can see Celsius is going to cancel, and grams is going to cancel, leaving me with a number in joules, and that is going to come out to be 55.5. Hang on, wrong calculator. Times 2.27 times 140.77. So 17735 is probably enough joules. Okay, in order to add that to my Q melt, I'm going to convert that to kilojoules. Okay, so 1 kilojoule over 1,000, 10 to the 3 joules. Okay. Oh my gosh, getting crazy with my shift key here. Okay, so that's going to be 17 point, let's see how many sig figs I know. 17.73 is probably enough kilojoules. So for section 2, Q melt is 8.4. And then for section 3, Q liquid to heat to whatever it was, 45.5 is going to be 17.7. So our total Q is going to be Q melt plus Q liquid. So that is going to be 8.424 kilojoules plus 17.73 kilojoules. So I don't know what it turns out to be, plus 8.424 is going to be like 26 point blah. How many sig figs? 3 sig figs. So 26.1589 blah 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 kilojoules. So the 3 sig figs, that's going to be 26.2 kilojoules to 3 sig figs. Okay, so with these kind of questions, obviously there is quite a few different combinations that it could actually be. You have to read the question carefully to infer if you're starting out with a solid or a liquid or a gas, and then if you are heating or cooling, if you're going through a phase transition, if you're going through one or more, right? So you're going to have to pick out what sections of the heating curve you're actually using, and just be really careful with units. The tricky things to look for is if you have molar heat capacity or specific heat capacity. So make sure molar, you multiply by number of moles of your substance. If you've got specific, multiply by your mass of your substance. Watch out Q, if you're using heat capacity, is going to come out in joules usually, okay, because those constants are joules per grams per Celsius, or joules per mole per Celsius. For delta H of fusion for melting, or delta H of vaporization for evaporating, you're going to be looking in terms of kilojoules per mole, so your Q is going to come out in kilojoules, and of course you're going to be multiplying by number of moles that you actually have, so you're going to need molar mass to work that out. And the other thing I should mention is that specific heat capacity, molar heat capacity, it does matter what state of matter you're in. It's different for the liquid versus the solid phase, etc. All right, so hopefully that's